Welcome everyone to Lecture 6, Intro to Space Navigation 2025 edition. Green here. Last class, there we go. Last class we talked about star trackers. That's our new unit, is star trackers, how to use a camera to determine your orientation in space. And I think probably I tried to do too much in one lecture because we didn't get through all my lecture notes for lecture 16. So really today is the last part of lecture 17 and then a relatively short, or sorry, today is lecture 16 part 2 and then lecture 17. Lecture 16 is just really long. But lecture 16, as a reminder, this is a 4-lecture series. Lecture 16 is on how to use a camera to determine line of sight directions to stars, right? Because we don't really care so much about pixels as navigators. We care about line of sight directions. So there's a star that way, there's another star that way, there's another star that way. And that, as you can see, is a little bit more complicated than it might sound like. We use the pinhole camera model, and we use the Brown-Conradi distortion model to go from a point on the image plane. Well, we start with a point in pixels. So you've got a star at 20, 30 in pixel space. We undistort that, we use the intrinsic matrix, and we ultimately get a problem, and we get a unit vector in the camera frame. And I also touched very briefly on camera calibration. If you're curious about camera calibration, I've got some great papers that you could look at for your project. That would be, I had, I think, 2 students last year who demonstrated some camera calibration MATLAB code for their project. That would be a great idea. But this is something that happens in labs, optical navigation labs all the time. Like, okay, I need to understand the intrinsic and distortion parameters of my camera, as well as its alignment, its attitude transformation matrix with respect to the rest of the vehicle, right? Because really, from a nav standpoint, we kind of want to know the orientation of the whole spacecraft, not just the orientation of the star tracker. So there's kind of extra steps that we need to do. So we're going to finish up today by talking about image processing, and then we're going to get into lecture 17, which is a star map. So the very idea that we're using stars to navigate implies that somewhere we have pretty detailed knowledge of where all the stars are, or maybe not all of them, but sufficiently many that we can navigate. And that is the case. There are some pretty well fleshed out star maps that we can use, and we can compare the vectors that we get in our camera frame to vectors that we get in the world frame, in this case, the International Celestial Reference Frame. That's where we'll be at the end of the day today. Next class is going to be one of the trickier bits of content, which is, okay, just because you have stars in one frame and stars in another frame, you haven't identified those stars yet. You don't know which constellation these 3 stars belong to. So this is the data correspondence problem, which is very tricky. But after we've solved star ID, now we know, oh, here's 3 stars in my local frame, here's 3 stars in the global frame. Because it's the same unit vectors expressed 2 different ways, then we can find the frame transformation from local to global. That's called Waba's problem, and that'll be lecture 19. I like to refer back to this because this lecture series is going to get a little bit intense, and I want to make sure that we're tracking. So today we're back to talking about getting stars out of images. And I kind of skipped over some important steps. So I talked about how to go from pixels in an image to stars to directions in 3D space, and that's this. This is the reverse mapping problem. We have all the equations to do this. We start with pixel coordinates. We apply the intrinsic matrix, but the inverse of the intrinsic matrix to get points on the image plane. We take care of the point distortion using the Brown-Conradi these equations. And once we have an undistorted point, we can normalize it to get a unit vector in the camera frame. But on homework 4, I'm going to give you a star field image and say, you tell me all the bearing vectors in the camera frame. And it's like, well, wait a minute. How do we get the stars in the image? Like, I'm just assuming that you found them and you have the pixel coordinates. That's a bit of a jump. So we're actually, I guess maybe I did part 2 first, and now we're going to do part 1, which is how do we do star field image processing. So starting from a star field image, What do we do to it? So there are, recall that a digital image is nothing more than a matrix of numbers which is the brightness at each pixel. A star field image which is typically black and white, is almost all dark pixels with some bright starlit pixels. How do we find star pixel coordinates? So the first thing we're going to talk about is thresholding, or you must be this bright to be a star. So the idea behind thresholding is set all pixels below some value to 0. Set all pixels above some value to 1. Or I guess 255. Basically, all the way dark or all the way bright. And then some value can be found experimentally. And I recommend 10 out of 255 on homework 4. So imagine you have a histogram pixels, and I'm going to erase this in a second. This doesn't belong in your notes, but if you have a bar graph of like brightness on the x-axis or intensity on the x-axis, and then just frequency of occurrence on the y-axis, it's going to look like this with like a little dip, that sort of thing. Almost all of your pixels are going to be black. So there's going to be a huge stack up here. And there's going to be fewer and fewer pixels as you get brighter and brighter. And then you'll get a little bip. And then these are the scarce pixels around the image, which represent stars. And generally, we just pick a point right about here, or it could be right about here, depending, and say, okay, everything dimmer, bring it down to 0. Everything brighter, bring it up to 1. And this is going to basically increase the contrast in your image. You're going to get some nice sharp stars. The reason we do this is for the next step, which is called connected components. Which is a neat trick from image processing. And I should say, by the way, image processing is worth its entire, well, it is. So it is its entire own course. and going through and the fun tricks that you can do with images and image processing. There is a great lecture series that another RPI professor, Rich Radke, he put together some lectures that he posted on YouTube that anybody can go and watch. I'm going, like, this is going to be the bare bones, like just enough image processing to get you through homework 4. But if you think homework 4 is fun, then I would encourage you to go study image processing as its own topic. There's a lot of really cool stuff that you can do. And then after that, you know, that kind of leads into like computer vision and like machine learning and all that. There's some really cool stuff you could do with images. But one of the most basic tricks in the book is connected components. And the idea of connected components is find all clusters of bright pixels that are touching one another. And can enforce size constraints. And when I say touching one another, you could have something like this, where let's say I found a bright pixel, and then there's another bright pixel right here. I'm now considering those to be members of the same cluster. And if you consider all 4 neighbors to a pixel, that is said to be a 4 connected component, north, south, east, and west. However, if you also consider the diagonal corners to a pixel, that is said to be 8 connected. And there are OpenCV and MATLAB functions that do this. So you could say, okay, here's my original star field image. Everything dimmer than 10, make it 0. Everything brighter than 250 or than 10, make it 255 or make it 1. Then we run connected components, and that's going to return a structure which gives you, okay, here are all the bright objects that I found. And then you could say, okay, well, all of those bright objects, some of those are just going to be noise, which is really annoying. So you could say, I require that all of my stars have more than 4 pixels. And we'll talk about that in a moment. But what I would definitely recommend on homework 4 is you say, for example, remove from consideration any connected components or blobs. Connected components sounds fancier than blobs. With too few pixels. And then keep the ones that have enough pixels. I think I said 4 or 5 for my minimum number of pixels, but you can play around with that and see what you get in your image processing. So, okay, great. What this will give you is the location of all of the pixels in an image which are known to be part of a group. But that still doesn't really tell us where the star is. So the last part is centroiding. So let's see. Yeah, we could talk about this here. Okay, so for a moment, you might be wondering to yourself, why am I treating stars as though they take up more than 1 pixel? Wouldn't a well-focused camera have like 1 bright pixel for your star and then you're good to go? So, well, that's not actually what happens with star trackers. We actually get blobs of pixels where 1 starlight is kind of spread out over several pixels. And that's done on purpose. And I want to have a quick aside and talk about why we do that. So for a moment, consider a theoretical perfect camera. I guess space camera. So this would have no distortion, no aberration, no noise. It would be perfectly calibrated. And it would also have a continuous focal plane array. Or in other words, no pixels. Because pixels mean that we have a discrete focal plane array, that below some size, you kind of lose all information. Right? A continuous focal plane array, you can zoom in forever and it'll never look pixelated. Right? This camera, such a camera, would still not see a star as a flawless point source of light. Instead, it would detect the Airy pattern caused by diffraction at the camera aperture, or we'll say entrance pupil. So I'm going to draw, necessarily feel the need to put this in your notes because I'm going to erase it, but basically you would get this kind of bullseye shape, which is the two-dimensional version of the diffraction spikes that we might be used to seeing in like the single slit experiment. So if you've got light coming in through a single slit like this, we know that we're going to get diffraction spikes when we have a grating that we read it on. In 2 dimensions, you get this kind of bullseye shape. So there's going to be a bright blob in the middle, and then it darkens, and then there's going to be a brighter ring, and then it darkens, and then another brighter ring. It looks like a little dartboard. Well, not quite like a dartboard, but a bullseye is a good way of thinking about it. So that's what we would get if we had a perfect camera. So, and I say digitally perfect, I guess not quite optically perfect, because we're assuming that there's going to be some diffraction. Okay. If a detector, and there are cameras that are good enough that you can detect an Airy pattern, if a detector is sufficiently sensitive to resolve an Airy pattern, the problem of finding the centroid of the star, centroid means center of the star, is called diffraction limited centroiding. So think telescopes. You can have telescopes that are so sensitive that when you point them at a star, you can actually see the diffraction pattern of light coming through the entrance pupil. And then when you're trying to find the center of that star, then you need to say, okay, well, here's our Airy pattern. Let's try to find the middle of an Airy pattern. That is diffraction limited centroiding. That is not what we have on a star tracker. So navigation cameras generally don't have this problem. They're much less accurate. So instead, a star point spread function or PSF will appear pixelated. Which gives us detector limited centroiding. So is the weak link in the chain your optics or your electronics? Generally, for navigation cameras, if it was perfectly well focused, the whole airy pattern of the star would fall on a single pixel. You would get one bright pixel, and then you're done, because that's all we have is one bright pixel. We can actually do a little bit better than that. So we actually don't want a camera to be too well focused. And I'll draw you a picture here. Actually, you know what? Let me try using the little rectangle trick. Oh, this is about to look so good. Yeah, right. Can I do a parallelogram? Well, am I being silly and just losing? Yeah, I am. I don't know why. Sorry, long day. Ah, there we go. Let's say here's an image, and then here's another image. Okay. And let's say that in this image, we've got one bright pixel. And then, oops, that was not my goal. Sorry. Okay. In this image, we have one bright pixel. In this image, we've got not just one bright pixel, but one super bright pixel. But then, you know, in this case, this is going to be like a negative, right? So generally, this would be a black image with a white pixel. I don't have the time to draw it all out that way, but imagine that in the one case, you have a perfectly focused camera. So this is perfectly focused. And this is intentionally defocused. Maybe you see where I'm going with this. On the intentionally defocused case, you're going to get one crazy bright pixel, which in this case would be dark. And then you'll get some less bright pixels. And then you get some barely bright at all pixels. Maybe it goes like that. If I say find the centroid, you are basically forced to say, well, there's one bright pixel. I'm going to take the middle of that bright pixel as my centroid, and we're done. Which means that you're accepting some error, because like, what if all the starlight is in the bottom right corner of the pixel? Or what if all the starlight is in the top left corner of the pixel? You won't know the difference. But if you defocus the light or the camera, you allow some of that light to fall on the neighboring pixels, and it actually gives you more information. So how about now? And some people have spent a long time thinking about the best way to solve this problem. But honestly, one of the first methods that will occur to you is what is mostly done on star trackers, which is just do a weighted average of all these pixels. Say, okay, well, the centroid is definitely in the same bright pixel, but because its top right neighbor is dimmer than its top bottom left neighbor, or sorry, other way around, its top right neighbor is brighter and its bottom left neighbor is dimmer, we know that the starlight is kind of towards the top right direction, if that makes sense. So to be clear, we intentionally defocus star cameras to get more information. The light falls onto a single pixel. We must take the middle of that pixel as a centroid. if light also falls on neighboring pixels, we can find the centroid with sub-pixel accuracy. There are several fancy star centroiding techniques. So like fit a Gaussian to it. I've also seen neural nets deployed here. But in practice, we often do a simple center of mass calculation. Which is just a weighted average. So it would look like this. U centroid is the sum over all the pixels in some region, or all the pixels that are within some connected component of UI intensity I divided by the sum of the intensity. And then V centroid is the sum over all pixels within some blob of VI intensity I divided by the sum of intensity. There we go. And that's it. So you would do this for all pixels in the connected component. And when we do this, we can generally achieve one-tenth of a pixel, or 0.1 pix centroid error in this way. So just by blurring your camera on purpose, you get this pixelated point spread function. You take the center of mass of all of the pixels that are brighter than some threshold, and then you'll get the pixel, the centroid of the star to within a tenth of a pixel, which is a lot better than we could have done if we had a perfectly focused camera. Great. And there's one final topic, and then we'll be all done with our image processing discussion, and that is bearing error. Pardon me, bearing error. So we haven't talked about bearing error yet, but remember that the goal of this lecture, like right now, we are ready to basically wrap up the lecture because we've said an image, you threshold the image, you looked at the connected components. For each connected component, you do a center of mass calculation to get the centroid. Now you've got a star in pixel coordinates. Then you do the reverse mapping problem and you get the bearing vector or the line of sight vector in the camera frame. That's the goal of this lecture. But because we're navigators, we don't just want an answer, we want an answer and our uncertainty. So we want a sense of how wrong our bearing error, or sorry, the bearing error is a sense of our uncertainty in our line of sight direction. So how does that come from pixels? Now, here's how we talk about that. Star line of sight bearing error. So what does 1/10 of a pixel centroid error, centroid uncertainty mean in terms of angular uncertainty? in our final vector, EI cam. What's the relationship? Well, you could just say it's 1/10 of a pixel uncertainty. How many degrees are there in a pixel? We haven't talked about that yet, but the angle swept out by an individual pixel is called the instantaneous field of view. Or IFOV. Or I'll hear people say IFOV. Okay. So if we know IFOV, then the bearing error, which is the same thing as the angular uncertainty, for a star line of sight is simply 0.1 pixels times IFOV. So then the question is, well, let's say you've got your camera. We're going to look at this as kind of a projector in a top-down sense. If this is your field of view, so you can think of this as a top view. If this is your field of view, we'll call this your horizontal field of view, because you could also have a vertical field of view that's different. Generally, if you're taking a rectangular, well, that's meant to be a rectangle. If you're taking a rectangular image, you're going to have a vertical field of view and a horizontal field of view. So we're talking about horizontal field of view for now. And then if this is the width of your image, which is just the number of columns in your image, then this distance, the distance from your focal point to your detector, is going to be your dx, your focal length expressed in pixels. So let's clean this up a little bit. If we turn this into a half right triangle, then this is going to be n number of columns divided by 2. This is going to be your horizontal field of view divided by 2. This is going to be dx. So this is where the equation from. Remember, we said here, number of columns, field of view, dx. You can say that dx, I'm just going to grab it from here. Dx is just the number of columns divided by 2 tangent of your, I guess this should be the horizontal field of view, divided by 2. But then we could take another triangle and we could say, okay, let's talk about a single pixel. And I tried to make this kind of skinny. Let's say this is just 1 pixel, and then this is dx. What is this angle? Well, this would be your IFOV. So from there, we can say that the tangent of your instantaneous field of view is opposite over adjacent, 1 over dx. So instantaneous field of view is your arctangent of 1 over dx. We're assuming for a calibrated camera, the dx would be given to you, so here we are. So the angle swept out by 1 pixel is your instantaneous field of view. If we're saying that our bearing error is 1/10 of 1 pixel, then it's 1/10 of your instantaneous field of view. And so now we can say, aha, from my star field image, I can use these basic image processing techniques. I can find the stars in the image. I can find the centroids of the stars in the image. I can map those pixel coordinates back to directions in 3D space. And when I hand this off to the next step in the process, I can also keep track of my uncertainty, which is just going to be a function of my detector. All right. So now we're done with lecture 16. You can see how that was kind of a long one. Thankfully, the stuff on the star map is going to be quite a bit shorter. But let's pause here. Any questions, or are we feeling okay? Okay, let's take a 5-minute break. So it's going to be 6:52 for you. Let's take a break. Back at 6:57, and we should have about maybe 30 to maximum 40 minutes talking about star maps.
Sorry, I was a bit late to this lecture. I had a bit of a moment, forgot what day of the week it was, and it suddenly jolted about 6:30. Oh wait, it's Thursday.
Oh, no worries. You are good. And of course, I'm going to post the video later. But yeah, we just finished up our discussion of image processing, which is a really more of lecture 16. So I'm going to repost these notes. And then after the break, we're going to talk about star maps, which I really only have about 2 or 3 pages of notes on that subject. So we won't be at it for too long.
Yeah, I got in just as you were talking about Sandshredding, so I've got from there down,
Okay,
and I can just check the notes afterwards.
cool. Sounds good. Okay, welcome back. So we'll spend the rest of the lecture talking about the lecture 17 topic, which shouldn't be too long, which is stellar cartography. Cartography just means map making or chart making, chartography. So here's the question. Where are the stars? How do you even make a star map? So you can imagine you're looking up at the night sky, but it's kind of tough to state the direction that a star is because it's moving. But the thing is, well, really, it's not moving because you're on the surface of the Earth and you're moving. But then, really, it is moving because even with respect to inertial, pardon me, with respect to inertial space, stars are moving, right? Each star is moving in the Milky Way, so on and so forth. So, how do we do this? So, what we can do is we can say, okay, at some moment in time, this star was here. Okay, well, what is here? Well, basically, we need is we need a list of stars and associated info for each. Okay. So what type of information do we want to know? And I'd like this bit to be interactive. So if you have any ideas, key in your microphone. What would you want to know about a star for your navigation star map?
Its right ascension and its declination, and probably its brightness.
Yeah, absolutely. So right ascension and declination are angles with respect to the International Celestial Reference Frame. So we're going to get to that in a second. But basically, you know that the line of sight to a star, even if it is moving with time, you knew it at some time. So we'll want the angle, the horizontal and the vertical angle describing where a star is in the inertial frame at some time. And then also, yeah, its brightness, typically expressed as what's called apparent visual magnitude. That's important. Is there anything else we can think of that you might want to know about a star?
Position of the star relative to other brighter stars that are probably easiest to notice.
Ooh, okay, I like that. So in that case, kind of, that's baked into uh, your definition of your reference frame. So we're assuming that, okay, your stars are defined with respect to some reference frame, but then the reference frame are defined with respect to very stable points of light in the sky that themselves are generally not moving very fast, pretty repeatable. So yeah, relative coordinates, I could see that. But I was saying before that the stars are moving. Wouldn't we like to know each star's motion? That'd be nice. Now, you might say, why don't we just get the position and the velocity of each star and be done with it, right? And the answer is, well, we actually don't know. That's the tricky part. We don't know the position of the stars. We know its direction with a great degree of precision because telescopes are great at direction, but its distance is pretty tricky. And we're not really going to go into a ton of detail on this, but the best technique that we have for measuring the distance to a star is called parallax, which is over the course of a year, the stars will move just a tiny bit with respect to kind of the background field of stars. Nearby stars will appear to jiggle a little bit because the Earth is moving. It's a little bit like how if you look at a point in the distance and you close your left eye and you close your right eye, it moves a little bit. That's parallax. Imagine looking at a star in March and then looking at that star again in September. And then 6 months later, you've got this nice baseline of 2 Earth orbit radii or 2 astronomical units. Even that will only work for the very, very closest of stars. And most stars are so far away that even that technique doesn't work. And then you need to get into some really fancy astronomy stuff. But if we were just going to throw away all stars where we didn't know mistake, because there's a ton of great information on stars. Essentially, my point is you don't need the distance, but you need the direction and you need its angular velocity. And that's basically what we need for our star catalog. So back to notes. Among other things, a star catalog contains apparent brightness for each star, typically given as visual magnitude. Or apparent visual magnitude. You'll often see Vmag thrown around. And with apparent visual magnitude, smaller number equals brighter. So it's one of those inverse log scales, where as you go brighter, a magnitude 1 star is brighter than a magnitude 2 star. Generally speaking, the limits of what you can see as a human on a really clear day is about 6. So if you're, at the Grand Canyon and there's no light pollution, you can see all the stars brighter than apparent magnitude 6. If you were, say, at, downtown Houston or downtown Albany, New York, and you are looking at the night sky, you might see only the very brightest stars because of the light pollution, right? That sort of thing. So there's also limits. I think the Hubble Space Telescope can see down to like 15 or something silly like that. I don't know the exact number, but it's very sensitive. Yes?
Oh, I was just gonna say I think it's closer to like 20 because I know for the fact Gaia has astrometry for stars down to about 2021.
Oh,
So I'd
fantastic.
imagine
Actually,
Hubble's on that sort of order.
yeah. Although is Gaia? No, actually, I imagine you'd be right. So I'm getting ahead of myself because I do have a discussion on that coming up. We mentioned Gaia. But yeah, I think then there's a question of like catalog completeness versus like, well, we got some stars that are that dim, but not all of them. But yeah, point being, smaller number is brighter. So for example, I think Venus, which is the brightest thing in the sky after the Earth after the sun and the moon, Venus is, I think, around about -3 on the scale. I'd have to go and check the exact number, but it varies, of course, based on phase angle and all that. But a very bright Venus would be a -3. And I think the brightest star is about 0 or -1, which I believe is Sirius. The dog star is the brightest star. I really should have this stuff written down before I just start rambling. Well, here, let's keep taking notes. Among other things, a star catalog contains apparent brightness for each star, as well as what are called astrometric parameters. Astrometric, star measuring. Astrometric parameters to deduce an inertial line of sight. Some examples of catalogs include Yale 1950, Hipparcos, and Gaia. Generally, Gaia has more stars and focuses on the dimmer ones. So it's closer to a complete sky survey. And then Hipparcos is fewer stars, but brighter. And you might say, from a navigation standpoint, we want as many stars as possible in our catalog, but that's actually not the case. You want a reasonable database search problem later. And you want the stars that are nice and easy to observe. So we're actually going to focus on Hipparcos in this class. That's going to be our friend. So the Hipparcos catalog which was published in 1997. I was alive. I don't think any of y'all were. Has 118,218 stars, ranging from negative 1.46 is the brightest, so that's got to be Sirius. M is a visual apparent magnitude, and the dimmest one is 12.4 in Hipparcos. We're not going to go even anywhere near that because our navigation cameras are generally not that much more sensitive than the human eye. So we'll say apparent magnitude 6 or even 5.5 is a good point to cap it. The Gaia catalog, data release 2, published in 2018. Pretty sure we were all alive in 2018. Has 1,692,919,135 stars. Ranging from 3 is as bright as it goes, and it goes down to 21. And basically, the dimmer you go, the more stars there are, which makes sense because you're basically looking not exactly further, because there are dim close stars and there are bright far stars. But generally speaking, you get an exponential increase in the number of stars that you can see as your detector gets more and more sensitive. So there are many, many, many more dim stars than there are bright stars. For bright stars, the brightest ones, you're generally in just a few thousand stars. And you've got, pretty much all of the ones that a human could reasonably see in the night sky. So the standard model this is the big kind of math. Both the Hipparcos and Gaia catalogs fit to standard model, which it seems bold to call something the standard model. That's like the normal distribution. I think maybe we should put some last name to it. But basically, there are 6 astrometric parameters. Which are alpha, which is your right ascension, and delta, your declination. So these are your horizontal and vertical angles described to the star in the International Celestial Reference Frame. But then there's also angular velocity. So we're going to say mu alpha is your right ascension proper motion. And then there's also mu delta, which is your declination proper motion. So these bits are angles. These bits are angular velocity. Not in degrees per second, but in milli-arc seconds per year, generally. So very, very, very small amount of motion of these stars. And then there is this weird variation on, it's theta? I don't even remember what the original symbol is. But this is your parallax angle. And then you've also got mu r, which is radial proper motion. So you don't get angle, angle, distance. You get angle, angle, parallax angle. So parallax angle would be related to your distance based on some trigonometry. And then you've got angular, so angle dot, and then finally mu r, radial proper motion. That would actually be in like kilometers per whatever year, that sort of thing. And so this would be radial information. And essentially, this is polar coordinates and range, kinda. That's essentially what we're getting here. So how do we actually, I talked about this, the whole point of the star catalog is to be able to deduce an inertial line of sight direction, to say, okay, for the ith star in the catalog, here is its line of sight vector in the inertial frame. That is our goal for today. We can define a right-handed coordinate system for each star in the catalog. Okay, and the idea is we'll say, okay, origin is at the solar system barycenter. I'm going to say that the L direction is along the line of sight. The P direction, we got to be careful. This is not the P from parafocal reference frame coordinates. Sorry, I know that's confusing. P is the right ascension direction, so the direction of increasing right ascension. This is going to make sense in a minute when I draw a phenomenal diagram. And then Q, again, not the, this is not your quaternion, and it's not the Q from parafocal reference frames. We're running out of letters, sorry. Q is declination direction. Okay, so what do I mean by this? Let's say that you've got the sun. I'm going to try to do some fun color coding here. So here's the sun. Maybe we'll color it in. There you go. And then here is the International Celestial Reference Frame. So X, Y, Z, and this is the ICRF frame. Okay. So then we've got here the equatorial plane. You know what? I don't know that I like that. Can I do an ellipse? Is it going to look good? Oh, yeah. Oh, now we're talking. Okay. There. This is our equatorial plane. And let's say that the star that we're interested in is out this way. So here's our direction. Okay. So what I'm going to say is that this star is going to have some projection of its line of sight along the XY plane. So I'm going to use, let's use green for right ascension, which kind of feels green today. This angle here is alpha. And then I'm going to use red for declination. It was Christmassy. This angle is declination or delta. Okay. So now, let's see, running low on color. Let's use blue. There we go. This line of sight direction is going to form one axis of this new coordinate system, which we'll call the L direction. Okay. Then there's going to be the P direction. Let's scoot this down a little bit. And then there's going to be the Q direction. L, P, and Q. Hopefully you can see that L, P, and Q is a right-handed coordinate system such that P cross Q is L. So you can think of P as like the X direction of this new frame, Q is the Y, and then L is the Z, where P is the direction of increasing alpha and Q is the direction of increasing delta. That's the idea here. And so L is, you know what? Let's do this. I'm going to try to get fancy footwork with my coloring here. Let's see how this goes. So L is cosine, cosine. I'm only doing this because the color coding is going to get annoying if I don't. Cosine, sine, and then sine. So the X direction, this is going to look really familiar because alpha and delta kind of look a little bit like our latitude and longitude. So that was not my plan for today, but that was our discussion right before the lecture recording started. It's going to be the cosine of delta, cosine of alpha, sine, and then this is going to be delta, delta, delta. That's the idea. So if your delta and your alpha is 0, then your L direction is aligned with your X direction. If your delta is 0 and your alpha is 90, then your line of sight is going to be along Y. And if your delta is 90, your alpha doesn't really matter. Now you're up along the North Pole direction. Similar idea. And then from here, P and Q are, this is going to be 0, 0, 1 crossed with your L direction, and then take the final vector that comes out of it and normalize it. That's the idea. So you can think of it this way. The Z direction, or I guess you could think of it as the ICRF, yes, ICRF Z direction. Z crossed L would give you P, but not necessarily a unit vector, so you have to normalize it. I guess you could also have written this as Z crossed with L divided by the norm of Z crossed with L, if that makes more sense. Either way. And then Q is just going to be, let's think about it. If P cross Q is L, L cross Q should give us P. There's our PQL direction. And you might say, Paul, why do I care, right? Isn't L what we're after? Isn't L the line of sight direction? It's like, not quite. There's more work to do. I wish it was that simple. Because we're not done yet. What direction is the star? Well, it's moving. And there are perturbing effects. Okay, so first we'll talk about line of sight perturbing effects. And then we'll talk about relativistic line of sight perturbing effects. Okay. The first is time delay, which is sometimes referred to as Romer delay. So line of sight is defined at the solar system barycenter. But what if the spacecraft, because remember, we're assuming this is a star tracker on a spacecraft. Generally, your spacecraft is not inside the sun. And if the spacecraft is closer to the star than the sun or further away from the star than the sun, there might be some type of a perturbing effect. So what if the spacecraft is ahead or behind? Okay. So the way I'll write this out is here's the sun. Here is the line of sight direction that we care about. Here is some spacecraft at position R. With its little star tracker. Here is the incoming starlight, which is generally opposite the L direction. And what we're going to do is we're going to say, well, look, here is the component of the position of the spacecraft that is basically along the line of sight direction. This is going to be L transpose R. As drawn to the right, the observer time is ahead of solar system barycenter time by a tiny amount. So we'll say this, T solar system barycenter is T observer plus 1 over the speed of light times this component of position, right? It's going to take light that much further to hit the solar system barycenter than it is to hit the spacecraft. So we do need to account for that. This effect typically perturbs stars less than 1 micro arc second near Earth. So generally way less than we can reasonably measure with our star trackers. So to be clear, we've got a degree, which is 1/360th of a circle. And then we've got an arc minute, which is 1/60th of a degree. And then an arc second is 1/60th of an arc minute. And so a micro arc second is, let's see, 1 in a million of a 60th of a 60th of 1 degree. So milli, micro. Yep. 1/millionth of 1/3600th of 1 second, which is small. So we can largely ignore our time delay, but you know, it's something to take into account depending on the level of precision that you're going for. The next we definitely can't ignore, which is proper motion. So the stars have all moved since the catalog was defined. Some more than others. Proper motion is typically given in milli-arc seconds per year. So the idea is if the catalog was defined 10 years ago and we have 2 milli-arc seconds per year, then the thing has moved 20 milli-arc seconds since the catalog was defined. 20 1/1000ths of a 60th of a 60th of a degree. Very small, but large enough that we generally don't want to ignore proper motion, especially for nearby stars that are moving relatively quickly. So let's get some equations going here. I'm going to say that EI, which is the actual line of sight direction, is the line of sight that is caused by, so the original L direction, right? Plus some delta t. So this is going to be the solar system barycenter time minus the epoch time. So the time the catalog was defined. Multiplied by what? Well, what's happening? We're seeing three types of proper motion. Mu alpha in the p direction. So the right ascension proper motion is moving along p. Mu delta in the q direction. The declination proper motion is moving along q. And the radial proper motion, mu r, is moving along L. And then all of this is now not necessarily a unit vector anymore, so we're going to normalize it. Where this is the original LOS, this is the perturbed or actual, we'll say seen line of sight. This is the catalog start time. Say catalog time. And then all of this can be thought of as some delta t. And then all of this is our proper motion term. Go. If radial proper motion is not known, it is generally safe to neglect. Okay, the next bit is parallax. So in interstellar space, as we get moving far enough away from the sun, we could use a star's (3D) position to compute its line of sight. But remember, line of sight is generally, or 3D position is generally not that well known. So in the solar system, near the sun, we can treat parallax as a perturbing effect. So the idea here is this. Let's say we've got the sun, and let's say that we've got the star. So this is the L direction, or maybe I'll do this as a dotted line for now. This is the L direction. And let's say you've got a spacecraft over here at some position R. And as drawn, the spacecraft is a substantial fraction of an interstellar distance away from the sun. Now, this is generally not the case. This is kind of exaggerated for scale. So this would be some L prime direction. You're not looking in the same direction because you've moved. Now, this vector would actually be some unknown range times rho. This would be rho prime L prime. Okay. So what we're going to say is, in general, rho, the sun to star distance, is much, much, much greater than our spacecraft position. So then we can say that rho prime is essentially equal to rho. So we can say this. Rho L hat is basically R plus rho L hat prime, which means that L hat prime is basically L minus 1 over rho times R. So we need to account for this 1 over rho times R, which is based on our parallax, which would be a distance measurement. So in this case, we'll say where 1 over rho is the parallax term. And I'll say that, by the way, parallax, this works backwards. Parallax is how we estimate the distance about that. Okay, almost done. So if we combine Romer delay proper motion and parallax, we get the standard model, which is this. EI hat is, again, L plus T solar system barycenter minus T epoch. And then we've got mu alpha T plus mu delta Q plus mu R times L minus our parallax term, spacecraft position converted to astronomical units, where 1 astronomical unit is the distance from the Earth to the sun, and then normalized. So this bit here is radial proper motion. Which is optional. And this bit here is parallax, which is optional. And there will be stars in the catalog where you just don't have this information. But the bare minimum is your proper motion. And of course, you'll need your right ascension and declination. So right ascension, declination, both types of proper motion, that's kind of your minimum success criteria. And this is the standard model. Right. And I want to briefly talk about some other perturbing effects, but I don't want to go into any gory detail on them because they're not on the homework and because I think we've gone over enough for today. So we're going to get the quick version. Relativistic perturbing effects. And we'll say at a glance. Because we're not even going to have any equations here. The first is gravitational deflection. Okay. Where essentially, we'll say this. Here's your spacecraft. Here is some massive body like Jupiter. Here's my best Jupiter. It's got like lines. It's got the big red spot. Maybe it's got like a thin little ring around it. And let's say that you've got a star, which is right here. Essentially, any massive body, even Jupiter or any of our planets, will cause some gravitational lensing, where starlight bends around the planet. Yeah, that's kind of extreme. But the idea is that the star looks like it's along this direction. Okay. So this is the actual star direction. This is the apparent star direction. So we'll call this EI hat prime, where prime is after accounting for gravitational distortion. We'll call this E to a body. So that body could be Jupiter in this case. And then this would be theta I body. And there's some really snazzy equations which would fill a whole page of notes to talk about how to go through and compute EI prime as a function of EI and the mass of the body and the location of the body and so on and so forth. And this turns out to be something that is large enough that you can't ignore it depending on your application. For a star tracker, this isn't going to be too massive, but it is something, if you're building a sensor that is specifically trying to measure stars to get something other than your attitude, pardon me, I think you will need to take this into account. And then the last is stellar aberration. Which I have a whole page of notes on stellar aberration. We're not going to go into too much detail on it. Stellar aberration clicked for me when I saw this diagram. So imagine that your telescope is like a little tin can. And then for the sake of expedience, I'm going to draw 3 of them. So here's another one. Nope. Here's another one. Oh, come on. There we go. Wow. Okay. And let's say that this direction is incoming starlight. Which will look like this. So let's say this is a single photon of light. But let's say that your instrument is cooking. It's this way. Then what will happen is, as you're moving, I'm actually going to move this along here. Scoot this over a little bit. Then your photon will be in the middle of your detector. And then in the end, your photon will be at the back of your detector. So the photon fell in a straight line, but your camera was kind of scooting along at quite some direction. And as you can see, the camera is picking up a photon in the middle of its sensor, even though it's looking this way, which I'm going to call EI double prime. When the true direction to the star is this way, which is EI single prime. For whatever reason, I can't draw arrows today. I'll try one more time. But you get the idea. So this is kind of an extreme. Oh, well, I lost the rest of my camera. This is kind of an extreme example. Obviously, your angle is never going to be like 45 degrees. You need to be moving at like crazy relativistic speeds. But the idea here is this is your line of sight direction to the star, but your camera is moving so much forward that you're going to get this different apparent vector. And this can be substantial. So the kind of metaphor that I think of for this is if you have an umbrella and you're walking in the rain, you hold it upright. But if you started to walk faster, you would need to move the umbrella forward, kind of rotate it, because the apparent direction of raindrops hitting you feels like it's hitting you from the front, even though the rain's coming straight down, right? So people who are running through a rainstorm and they have their umbrella cocked forward, they understand stellar aberration on a more physical level than we do. But you get the idea. And so I have a whole page of notes on the equations that take you from EI single prime to EI double prime. But I will mention that stellar aberration generally should not be ignored for a star tracker. The star trackers that we have, for example, on Orion, we take into account stellar aberration. It is something that's worth considering. And I'll also mention that it has been suggested that stellar aberration could be used to measure velocity. So rather than accounting for our velocity and putting a correction angle on all of our stars, what if we knew the stars to a great degree of precision, which is way easier said than done, and I'm going to hand wave over that. If you know which direction your stars are supposed to be facing, and you can measure the stellar aberration, you can actually figure out your velocity, and this is called StarNav, which would be a great paper to study for your term project if you're interested. But that is enough for now. I think we've gone over quite enough. So I'm going to wrap up. Any questions about lecture 16 or lecture 17? Otherwise, I'll stick around after lecture and we can talk about homework or anything else. Good stuff. Thanks, everybody. Class is dismissed, but feel free to stick around if you have any individual particular questions.